Okay, next one is the organic molecule, individual organic molecule. In this case, we have retina molecule. Everyone has your eyes. This is for photon detectors, why we can see the series through our eyes, because we have this molecule. This absorbs the photon, then molecular conformation goes to the transformation through the transtype, and if you shut off, then it's going back. So this photon detector. Okay? So each time molecule moves, then this the stimulation goes to the brain. Then we detect the light. So this is very important. Organic molecule. The point is it has been very difficult to image the individual organic molecule. Organic molecule is very weak, very fragile in the direction being irradiation. So immediately it's decomposed, no way to get images. But we found if we put them into this carbon nanotube, they can sense very well. That's why we have these images. Okay. These molecules attached to the C6 UCDs. And some of them may be bent, so this transtype, and the cis-trans and transformations. So this is first report showing the organic molecule, individual molecules. Then yes, this is just accepted to the JAX. This one is the again p-port. Only the one type, C70. Okay, so it's football. It's not a spherical. So it puts this one into the carbon nanotube. The two possibilities: to lie down or upright, because the diameter is different in the two directions. So then these are images. Okay. But what we're interested in the interaction between is the molecule and the carbon nanotube. I think this is a problem here, okay? And what kind of interactions are seen here? So distortion or charge transfer. And then our spectroscopist did careful experiments. I think it's too much, too detailed, but briefly I go. We have two types of nanotubes because we cannot have just one type of tube. So we have always, our specimen has some distribution. So two types means differently prepared. So one is this side we have more thinner tube. Right-hand side we have more thicker tubes, so distribution different. And then we put this C70, and then obviously if the diameter is too small for the C70, so before after inserting these, doping these structures, there will be no change. But the thicker one, they accept. Then also two-way, upright or lie down. So this is detected by looking at this, the photoluminescence, two-dimensional photoluminescence. I think this one is this one is different. See, this up, the top two are the C70, these are C60, and these are with the doping. And then we compare these two, the 70 and undoped one. These are very different. They both are different. And so you can see these figures. These are distribution of these two batches of the carbon nanotube. And then if you look at the detail, then you can tell what the interaction is going on. Okay. Another one is this is coronet. colonel is this molecule. Okay. So now this time we put the colonel into this single carbon nanotube. So you see this. I think these are individual organic molecules stuck. Then this one, you see this alignment is with respect to the nanotube. Angle is something like the 77 degree, okay? But the 60 or 46 degree, that's for the bulk, this coronal crystal structure. So crystal is always 45 degree ground. But if you put them into the nanotube, that's much standing up like that. So it's different. So obviously, a lot of interaction between the wall and the molecule itself, and then the molecules themselves. Then once again, we checked the luminescence and what's the effect from the strain or charge transfer between the nanotube and the molecule. And this is because these people, I think this is with the colonel in carbon nanotubes. I think this is just green. This is doped. This one is the hexagon. So obviously, this is actually blue and green. So there's a shift after doping. So I think in this way we can change so interactions or electronic structure both the column and also carbon nanotube by doping these molecules. Applications since we can put the carbon nanotube and the colony into carbon nanotube, and these are actually the bacteriophage. They eat this carbon nanotube, and then and of course carbon nanotube inside we have the colony. Then afterward we shine the light, highlighted these yellow regions are where we have the colonies. So in this way, maybe this kind of people might be markers for biological applications. Okay, I didn't go detail, but just I'm going to show you what we can do with this new material. Now the microscopy. These are the latest microscope. There are several different, three different ways to see individual atoms through the modern microscopy. This is what's called the dark field imaging, annular dark field imaging. Whereas I think the previous one is always outside. The vacuum is brighter than the inside. This contrast is reversed now. So brighter regions where we have better atoms. And then the 30 kV, 60 kV, we are lowered the accelerating voltage in order to see the carbonaceous material. Usually, commercial microscope operated at 200 keV, much higher. So the penetration is much stronger, but you lose contrast. So light element like carbon, you cannot use a high voltage microscope. And also, if you have a higher voltage, you increase the radiation, electron beam radiation damage. So that for certain application, we need lower the accelerating voltage microscope.